Get a good stretch in. All right. The calculus. All right, what are we at here? Do we have humans? More people are coming. Cool. How is everyone? Good to hear, Max. All right, it is Friday. So I wanted to start by talking a bit about the plan going forward. So you know, we've talked amongst ourselves, Pofald and me, and also like Dr. McKinney because he's doing Calc 1, and at least for us, I think we're gonna go no BSE. It's just not gonna happen. I mean, I kind of hinted at that before. I don't think I officially confirmed that there's not going to be one, but we talked about doing something different, like changing it a little bit. But like the whole retake situation, I mean, we thought of a way to adapt that a little bit, but it just seemed like too much work and like not enough benefit to you guys or to us, and so that's gone. We are going to have a test next week. I'm thinking Friday. And it will be like roughly class time. Like I want you guys to basically, I'll open the file around start of class time, and then I'll give you until like, maybe I'll start it a little earlier than class time since you guys are on the lunch part of things, so it can give you a little extra time. But basically, if you get extra time or something on a test and like have a class right after, you should talk to me beforehand. But the goal is basically to finish it in class time and then scan it. The huge issue, right, with like take homes, especially with calculus, since there are so many things out there on the internet with calculus, which is not as true for these other guys that I'm teaching, the more proof-based things. It's hard to write a test and like have a situation. Like I can't just give like a take home and say like you have 3 days to complete this. I mean, I could. But I don't think trusting is my strongest attribute as a human, and I just don't think it's useful to do that. So I think basically trying to finish it in class time and make like a reasonable test to do so is kind of the best way to do things. But the test is going to be kind of different than what you've maybe gotten used to with Calc 1 and Calc 2. My plan, and I'll give more information this weekend. I've only kind of flushed it out in my mind right now. But the idea is I want to look for the big skills, right? Like this is not an ideal situation. Learning is harder. I'm not going to have like a 12 question test in which like you have to remember like, oh yeah, there was that one thing he talked about for 20 minutes, like 2.5 weeks ago or something. Like we're not going to do that. There will be nothing on there that we only briefly talked about. My goal is to hit the major topics. Okay. So I'm not exactly sure how I'm going to break it down yet, but my guess is going to be it's somewhere between like 4 and 6 questions. Again, not promising this, but like fewer questions. Went out. And, so I guess fewer questions, but they go deeper. Right? So like you should know how to, so like an example, right, would be like a Taylor series question where you would actually have to go through and like find the Taylor series by hand and then maybe use one of those like substitution things after, right? And then like find Taylor for something similar function, like this would be part A, and then B would be like find Taylor series for some similar function using part A, right? So think back to the homework that I just graded last night, right? So you had like e to the negative 12x. Well, you use the fact that you know that e to the x is this, right? And then you just substitute the negative 12x in there for x, and you use this guy, right? So like that kind of idea, and then maybe ask something about error bound or interval of convergence, something like that. Convergence or error. And so basically, right, like I'm hitting Taylor series, boom, one long question, but then like that's everything on that. And then, something with, a few of the series tests for like, does this converge or diverge, right? A few basic improper integrals, because really we've covered a lot of material since the last exam, and I just don't think it's reasonable to ask you to know like every little thing, especially given the fact that like class has gone on this different format. So that's the plan. And like I said, I'll try to have something up by Sunday. I mean, like the current typical test questions that were up for like the exam that was postponed, definitely still useful. Very good practice. And I may not change the review much, but I'll give you more details in terms of how the exam will actually look, and what to expect by the end of the weekend. Any questions on that? I see Caleb typing. So are there still no notes? Also, will you still do a TTQ? What do you mean no notes? Oh, on the actual test. Gotcha. Yeah, so I would want you not to use notes in that case. I mean, basically, it would be like a normal in-class exam, just, I guess, more focused on big things and less like trying to get everything that we've done since the last test. Will I still do a TTQ? There are TTQs already up. For the postponed one, I may add a few since we've done a few things since then, but I think it was previously going to be up through 11.5, and this one would basically be up through 11.7 or 7.1. I haven't decided yet whether I want to include area between curves or not. Honestly, if you guys want to, if you're in the Twitch chat, or I guess here too, type 1 if you want 7.1. I can't spell. Holy crap. You want 1 if you want 7.1, and 2 if you don't. Because I can see arguments for either from your side. Right, because 7.1 is maybe easier than series, being area between curves. However, it's also another topic. We would not have the volume stuff, I don't think. I think that would be going a little too far. So I guess 7.1, this would be like arc length and area between curves. Okay, so I'm seeing some ones. So yeah, so I'll write up like an addendum to the study guide as it is, and the TTQs, I'll add a few things from the latest topics, but basically the TTQs that already exist should be pretty good for like 80+% of the stuff that we've done. Review session, absolutely. Review session we would do maybe Wednesday. Would be a reasonable day to me. Potentially Thursday. I'll send out a doodle poll like maybe next Monday or something to figure that out. So yes, there will be a review session. Wednesday or Thursday next week. Cool. Any other questions? Mr. Gigabounce. See Jackson's typing. If you have a mic, you can use that too. But all right, will the test just be through a submission during class time in Canvas then? Yeah, that would be the plan. And yeah, I'll have again more details by the end of the weekend. That's fine. No, you're good. Okay, so let's go ahead and actually get started on calculus. So we're talking more about volumes and then getting into like volumes specifically from revolving around axes. So I do have the 7.2 worksheet up, but again, as always, I will be writing the things out as well. So basically, we have a couple of options here in general, and so I wanted to talk about the one example from our class prep. Right, so it's like a sphere, and we want like the volume of a sphere of radius big R, because I saw some things that were interesting from this, and I also wanted to point out like the different ways you can set this up. Right, so this one is completely symmetric, which is why it doesn't really matter which way you choose, but in general it will. So you can do this in two ways, right? You can look at like what happens like flat on the plane, right? And so like I've drawn it in 3 dimensions, but really like you want to see it as this guy and then worry about the cross sections for your like 3rd dimension of stuff to fill it out. So I'm really thinking this picture to capture the one above. And then you can do cross sections either horizontally or vertically, right? And so if you have horizontal cross sections, you're looking at a general y value, whereas your vertical cross sections, right, vertical lines are defined by some x value. And so if you choose the horizontal, you're going to end up with some integral. What are your y bounds? Well, it's from negative r to r of your cross-sectional area at y. So, you know, here I'm choosing like this specific y, dy. And if you do the x, then it would be negative r to r as well. Again, this one is symmetric. Of a of x, so that's like, check out this cross-section here. At x, what is the area of my cross-section? Dx. And so in this case, right, my cross-sections are circles, right? I have like a circle's worth of circles, but they're of different radii. And so let's look at this one. Okay, so let's do the horizontal cross-section here. Oh wait, no, we did the horizontal in class last time. So let's do the vertical one. So this guy is vertical. Right. So I choose my x, and then I know my a of x is pi r squared. So I need to figure out like what is my r, right? So a lot of what I was seeing when you guys were going through this was you had this part, but then you kind of treated r as your variable. X is still your variable, right? This is dx. So we want to integrate with respect to x. And so what we need to do here is figure out like what is r with respect to x, or in terms of x, right? And so r is this, that doesn't look very good. I'll just redraw it. Right, so I'm choosing my x here, and then really this is my r, right? So I get a circle, and of course like the whole thing, it goes all the way down, but the radius is just this top half. Now what is the equation here of this semicircle? Because that gives me everything, right? Like this height, r, is equal to the y value on the circle at x. Right? Exactly this point. So if I know this y coordinate, I know my r. So what is my function? What is my y value there? I mean, I know some of you got this, so I should see some response. All right. This is where I wish I could just stare at you in class, but fine, fair enough. So this is a circle of radius r, right, or my sphere, but like this cross section here, I know that y squared is x squared plus my big R. squared. And so y is plus or minus the square root, or sorry, geez, other way around. My radius squared is this, and so y is plus or minus my big R squared minus x squared, but I'm looking at the top half, so I'm looking at this guy, right? I'm looking at the square root of R squared minus x squared. Okay, so that tells me my a of x is pi, and again, this is little r, times the square root of R squared minus x squared squared. And so this is just pi times R squared minus x squared, because my square root just goes away. Does that make sense? See you typing, Max. The stream keeps cutting out. From both of my monitors, everything seems fine. Is anyone else having it cut out? Okay. Okay, yeah. It might just be your internet. I know I have good internet here, so it's not surprising that mine's fine, because I still have the campus internet. Okay, so this is our general area function, and then, well, that's all we have to do, right? We integrate from negative r to r of this guy, and then you just like do the integral. You could also realize that these are symmetric and do 2 times the integral from 0 to r of the same thing. These would be the same using symmetry. But then from there, it's just do the antiderivative with respect to x. And so that part I'll leave to you guys if you didn't get that. But the setup is the most important for these. It's rarely the integration that gets you, and it's more the setup, because most of these integrals aren't too bad. Okay, so now I want to do one more example. So here I'm going to test my art skills. So I want to do the volume of a ramp, but I want to do it in a couple ways, right? So I'm going to have length 6 in the x direction, height 2 in the z direction, and width 4 in the y direction. So like, you know, I have a 3-dimensional shape. Oh boy. Yeah, that looks like a good XYZ axis. And so I said height 2. So I'm looking at like 2 here. So I've got my ramp there. This is 4. Right, so maybe I'll make that more clear, right? This is height 2. This is 4. And then it comes down here. Whoops. There at 6. So this is length 6. And then, you know, it goes out here. And so this is my like 3-dimensional ramp guy. Hopefully that looks reasonable. And so, right, like this is my y direction, my z direction, my x direction. And so you can kind of do this in a couple of ways. So I want you to look at it, one, with vertical cross sections. Or sorry, maybe I'll just be specific to the axis I'm talking about. Cross sections perpendicular to x, and then we'll do cross sections perpendicular to the y-axis. Yes. So if I'm looking perpendicular to my x-axis, right, then the way I view this is I'm just like, okay, well, what am I getting? I'm basically taking like vertical slices, so this will be the one in the red, right? I'm taking slices like here, down, that kind of go in the y direction like that. And so this I can just put in terms of like, here's my z-axis, my x-axis, and then I have these vertical cuts, right? And then what are my cross sections here? So if I look at like this x, what is my cross section? what shape will I get if I extend out in the y direction from here and take a cross section of my ramp. Yeah, you'll get a rectangle, right? So these are rectangles. And this is up at 2, this is over at 6. And so if I fix, this x, what is my cross section? It's a rectangle. My height here is what I need to figure out. My width is always 4, right? Because I'm going it's 4 wide, my ramp is. So this is important. So this is like some h. And then if we look on my other one, I'm just going to kind of set them up and do the same step for each. So here, if I do perpendicular to the y-axis, what are my cross sections now? So these are like the guys in blue, right? So I'm like cutting down like this. What shape will I get? Yeah, they are triangles. Good. Right, so like if you cut up like I have in blue, right, you're slicing it, you have the triangle, right, just like think you're going up a ramp and then you just like slice directly ahead. If you check out what that was, it is this triangle on the side. And why this is nice is, so here, right, this is what I have. I have like that as my backdrop, and then I'm getting things going in the x direction for my cross sections. But these are triangles. Now what's the difference between these things? So my cross sections here all look exactly the same, right? Because it doesn't matter where I am on the y, if I'm going along the width of my ramp, all of these triangles are exactly the same, right? They're all coming the same length down in the x, they're all going the same height. And so these are actually constant cross sections. This is always this triangle, right? Whereas these guys, as you go down the ramp, you have shorter and shorter rectangles, right? Your height is decreasing as you go down. But as you move along the ramp in this perpendicular to the y, you're actually not ever changing your cross section. So in this way, you can actually view it as like a prism, and it's much easier, right? So these are constant. Notice there's no variable involved here. Okay, so now we need to set up an integral. So this one is basically almost done, right? So what is this area? Well, it's just 6 times 2 over 2, right? 1/2 base times height. So it's going to be 6, and then we have 0 to 4 of ay dy. Well, that is just going to be 6y from 0 to 4, so we get 24, and we're done. Because that was not affected by our y value. It was just this same area on every cross section. But here, when we have differing height as we change our x value, as we go down the ramp, we need to figure out what h is. So does anyone have an idea of how to compute h here? You should think back to the class prep video for how I did the pyramid thing. There's a nice geometrical method here. So you know the big triangle, right? Big triangle has base 6, height 2. What's our buzzword here? It's proportional to the big one. Yeah, exactly. So similar triangles, right? So use similar triangles to find h. Right, so we've got our big height over 6, our big length, is equal to our smaller height over, well, how long is this? We take away the x, so it's 6 minus x, and so we get 6h is 12 minus 2x, and thus h is 2 minus x over 3. And so then our area with respect to x is going to be 4h, which is 8 minus 4x over 3. And then our x values, right, these are running from 0 to 6. So I would do 0 to 6 of 8 minus 4x over 3 dx. And let's confirm that we actually get the same thing, right, because this looks very different than the other one. So I'm going to get 8x minus 2x squared over 3 from 0 to 6. 0 gives me nothing. And so I get 48 minus 2 times 36, which is 72 over 3. Well, 72 over 3 is 24. 48 minus 24, also 24. Okay, so I just wanted to get practice looking in different directions. And as you can see, right, sometimes there's like a wise choice, because like you can just compare length of problem, right? The one on the right, if you take the one where you have the same cross sections throughout, it's just less work. So it's good to be flexible and not always choose x as your like default variable. Okay. Any questions before we move on to like solids of revolution? Okay. I guess we shall move on. All right. So this is what's called the disk method. And basically, right, the idea here is you take something. So let's look at, say, y equals 2x. Okay. So I have something that looks like this, right? It's a little steep. And we'll just say this is like 2, 4 up here. Then I can do a couple of things here. I can revolve it around the x-axis. And when I say that, that means I have this region that I look at. Right, I'm revolving a region. And so basically you take an area and then you just spin it around your axis, and like whatever you get from that is now your solid, right? So like take a circle, rotate it around, you get a sphere, or a semicircle, rotate it around, you get a sphere. If you do a circle with like a gap between your axis, right, you're going to get like a donut, stuff like that. And so here, if I rotate around my x-axis, I'm going to get, I'll change how I draw this a little bit. I would get this like cone shape, right, that looks like this. And so this is the goal here. But you could also have revolved it vertically, right? You could revolve around the y-axis as well, in which case you would do the same thing, except it would be up here. And you would get this guy, and the region you would have been talking about would have been like the region under the curve, but with the y-axis, right? So you're looking at like two different triangles. You're looking at, I'm revolving this area around the y-axis, or I'm revolving this area around the x-axis. And so this is a line that's fairly steep. Which cone do you think? Yeah, which cone do you think has the greater volume? The y one or the x one, or red or blue? Red or blue? What has bigger volume? Do we know the volume formula in general? So it's pi r squared h over 3, where r is like your base radius. So if you had to guess from this, which one do you think has the larger volume? Yeah, Charles, you are correct. The blue one has the bigger radius, right? And the radius is like double counted with regards to the height. So like the red one is taller, but the radius is squared, whereas the height is not squared. And so blue should have more volume. Let's check that that's true. So how do we calculate volume with the disk method? Well, the idea here is exactly what we had before. It's just that since you did a revolution, your cross sections are always circles, right? So like we had the example up here, right, where it depended on your point of view, but we got rectangles or we got triangles. If you do revolution, it's always circles. And so it's really just applying what we previously know to a very specific situation where you know the cross sections are circles. So, right, our a of x or a of y is always, pi r squared. You just have to figure out the r. Okay, so let's do, I'll redraw this. So this is y equals 2x. So first, let's do it with respect to the x-axis. So let's find the blue one. So if we revolve around this guy, then, I'll take some x here. I take my cross section. Then again, I'm going to get a circle. And this is my radius, right? This is my radius. Well, that radius is exactly the value of your function, right? And so my a of x is pi r squared, but this is always equal to pi times f of x squared. And so your volume in this case is, whatever your interval is, right? From a to b, here a is 0, b is 2, of pi times f of x, which is 2x, squared, dx. And so you end up getting, so this is 4x squared. So we get 4 pi over 3 x cubed from 0 to 2. And so we get 2 cubed is 8, so you get 32 pi over 3. Does that make sense? Before I do the y one, like, is that clear? What's going on there? You guys are very quiet. Okay. All right, so for the red one, right, so now we are going to go around this axis, my y-axis, and then I want to look at like my general cross-section here, right? So now I'd be looking at this guy, and so I check at y, and so I'm not using y equals 2x anymore, right? I want a function of y. And so I go from y equals 2x, I'm like, what is my height here? Well, it's really like view x as 2 over y, because really this is just, okay, so this is just your x value at y, right? And in general, again, your a of y is pi r squared, which is pi times like g of y squared. I don't know why I have 2 parentheses there. And so this as a function of y is going to be your radius. And so here x is 2 over y. And so my volume is going to be pi times 2 over y squared dy. And my y values don't go from 0 to 2. I go from 0 all the way up to 4. And so what do I get? So this is x is y over 2. I'm sorry. I know how to divide. Y over 2. So we get y squared over 4. And so when I go up, right, it goes y cubed over 3. And so it's like y cubed over 12 from 0 to 4. And so this gives me 64 pi over 12, or dividing by 4, I get 16 pi over 3. And so we see that indeed the blue is more. It's in fact double the volume. Okay? So those are actually not too bad, right? Like once you figure it out, I mean, it's really just figuring out like what is my radius, and just use the function that you have so long as it's with regards to one of the x or the y axis, and then just pi times that squared is what you want to integrate, right? So it's really just like plugging it in once you figure that out. So this is where, again, like drawing the picture, drawing that region is huge, and that's why area between curves was good practice. But there's more of a reason why area between curves was good practice. We don't always want to revolve this kind of region, right? It's not always going to border the axis that we want to revolve around, right? Because sometimes you actually want holes to exist. So, for instance, like let's draw this picture. Whoa. So let's suppose we have these two functions. So we start here at 0, 4, and then here's my like 2, and so y equals 2 just is there, right? And then y squared, or x squared plus 4 looks like this. And so, you know, I'll bound it, I'll say on like 1 to 3. So at 1, right, this is up at like 5. Clearly not to scale as usual. So we'll start here, and then we'll go here at 3. And at 3, right, this is going to be 13. And this is obviously still 2. So, you know, if I have this region, but I still want to revolve around the x-axis, say, what happens? What is the shape that happens if I revolve this region around my x-axis? Right, if it was bordering the x-axis, I would get something that looks like this, right? That looks ridiculous. I want the same way. Not the eraser. Yeah, that's fine. It would look something like this, right? But that's if it was bordering, right? If I directly bordered and then rotated around. What does this gap here make happen? Yeah, there's a hole, right? So it's like I get this piece. So it's basically, oh boy, can I draw this? This may have been a huge mistake. Yeah. Looks something like this. Yeah, this looks reasonable. It looks something like this, right? Where you like take that bowl and then you like remove a cylinder in the middle, right? You just like pulled that out, and then that's gone. We've holed this guy out, and we're good. And yes, I realize that I probably should not have made those hand motions. It's fine. Okay. So anyway, we can still talk about the volume of this guy, right? Like you can still fill this guy up. You can talk about its volume. So how might we do the volume? Well, think back to how we did area between curves, right? You'd like do this, and you'd be like, okay, I'll do this whole area. And then I'll subtract away the area underneath. Jeez, why does this always do everything, right? You just want this area, and so you take the whole stuff, and then you subtract it away like the stuff in red, right? And so the idea is the same. You could take the volume of this minus the volume of your cylinder that's removed. Okay, so basically you want to think of like it's an integral of one minus the integral of the other, just like you did with area between curves. So here, when our functions are y equals x squared plus 4, y equals 2, you want to think of, okay, I've got this thing. This guy is my outer radius. I'll call it r sub outer. And then this blue is my r inner. And so how do you get the volume? Well, again, if you revolve, it's still circular cross sections, and so it's the same basic idea. So this was on 1 to 3. So you want to do like 1 to 3 of r outer squared minus pi times the integral from 1 to 3 of r inner squared. And of course, you could bring these together if you want and do r outer squared minus r inner squared. Questions on that process? Does that make sense? So it's like basically doing the same thing as area between curves, but up a dimension. Questions? So in this specific case, right, we will get pi integral of 1 to 3 of your x squared plus 4 is your outer, that's the one on top, minus your inner, which is actually just radius 2, right, because it's the gap to y equals 2 squared. And then this would be dx, because I'm doing my x bounds. Okay? So we're gonna focus more on the setup right now, because again, like, yeah, you could square this out, you can do reverse power rule, I believe. So not gonna focus on that as much. So let's consider this example. Okay, how about revolve? So something else you might be concerned about is revolving. Every time thus far we've done like the x-axis or the y-axis, but like why? Right? You don't always have to revolve around a specific axis, right? So, you know, maybe I consider the floor like x or y equals 0, right? But maybe I revolve something around my desk, which is at like y equals 4, right? I'm not revolving around the floor because I like can't go through the floor, but maybe I like, you know, I'm for some reason wrapping rope around my desk or something. You know, you can do something around y equals 4 instead, and that's a different axis. So here, I want to rotate the region bounded by these two functions, so y equals x squared plus 2 and y equals 4 minus x squared, about the horizontal axis, y equals -3. So we should figure out what the picture looks like first before we can really grasp this, I think. So I want the region bounded by these. That means I need to find where they intersect, right? So my first thing is just to set them equal to each other, figure out what is this region. And so if I do this, I get 2x squared equals 2. And that's nice, right? X is plus or minus 1 then. So I know that's where they are going to intersect one another. And then I guess I need some room below. So where are they, right? So 4 minus x squared starts up here at 4. And here at x equals plus or minus 1, your y coordinate is 3. And so if this is 4, 3, 2, 1, and then here's my -1, here's my 1, then I'm talking about intersection points here and here. So this is my 4 minus x squared parabola. And then my x squared plus 2 starts here at 2 and then goes up. And so the region I'm talking about is exactly this region here. But then I want to rotate it around like down here. Right, this is my y equals -3. And so the rotation I'm doing is I'm taking that region and I'm rotating around this guy really far away. So I'm still going to get circular cross sections, right? I mean, I'm still doing a revolution. The question is, what is the radius? Well, before, right, we were doing like this axis, and you'd say like my inner radius is this, and my outer radius is this, right? Well, now you're doing the same basic thing, or maybe I should do this in different colors. So this is my inner, this is my outer. But all we've done is just extended what we're rotating about. So basically we just add 3, because we've gone 3 farther down below, to each radius, right? And so like my r outer is, well, how far is it from the x-axis? Well, it's 4 minus x squared, but then plus 3 for y equals -3 to y equals 0. And this is like y equals 0 to y equals 4 minus x squared. And so your outer radius is actually 7 minus x squared. And then your inner radius also adds 3. So the inside guy was x squared plus 2, also plus 3, or x squared plus 5. And so once you find those bounds are -1 and 1, you go -1 to 1 of outer, so pi for pi r squared times r inner, or sorry, r outer squared minus r inner squared dx, right? So this is r outer squared minus r inner squared. Thoughts, questions, comments, anything to show me that you are alive? Yeah, Mike sounds good. Yeah. Sure. Sorry, I'm going to mute you for a second just because my voice is coming through yours as well, and then I'll unmute you after I'm done talking. So the hardest things, I think, so things to look out for. Make sure you find the right radius. Right, so always count, like, how far is it, count distance from your axis to the graph, right? You don't care what the axis is, but start there, right? So like I'm looking at -3, I'm going up here, and then I'm going up again, as opposed to like just looking at the function by itself, right? Like I'm looking always from the perspective of the axis. That way I never screw up if it's a weird axis that I'm rotating about, you know? Because you can do a vertical one at like x equals 5, for instance. Then you should start there and think, how far am I away from that? What is my outer? What is my inner? You know, use that as your point for your point of reference for your perspective, instead of just the x and y axes. And then also, you should know when to use dy versus dx, right? So here, if it's a horizontal axis, like we just did above, then you have vertical cross sections, and so it's dx. And then the other way is opposite, right? So vertical axis, right? So if I have, you know, something like this, and I'm rotating around this, right? Then my region is this guy, and my cross sections are now horizontal cross sections. And so this would be dy1, and that means you would want to get your function in terms of y, right? That could be a potential issue. Those are the two things that I see screwed up most often. Any other questions? Or a follow-up if you have one? Okay. Well, if there aren't any questions, then I mean, I do have office hours starting, you know, nowish. So I'll be around in Discord if you're working on the homework or want to talk more about what we just talked about. And otherwise, I'm just going to go ahead and end stream.